In the last lecture, we had discussed about rule based expert systems, and we have also given the example of mycene. It was shown that mycene not only provides expert advice, but also interacts with the user in a very natural way, and often it is not possible to really distinguish between whether you are communicating with a real doctor or you are communicating with an expert system, a computer program for that matter. Now, today in our lecture, we will start discussing about uncertainty management. We have seen also in the case of mycene that the mycene rules often put in some suggestive evidence. For example, if the symptoms are so and so, then there is suggestive evidence 0.7 that the disease is so and so. Now, this suggestive evidence 0.7 or 0.8, whatever the number might be, is actually talking of some uncertainty or some weakness in the strength of belief of the expert in the conclusion. If we were absolutely certain, well, for example, if the two sides of a triangle are equal, then the triangle is isosceles. In that case, there is no uncertainty in this conclusion. However, because of several reasons, in real life scenario like medical reasoning, automobile diagnosis and many other things, we cannot be very sure about either the evidence, or if the evidences are known, its relationship with the conclusion. There is some uncertainty lying somewhere. In the next few lectures, we will see how such uncertainties can be handled in the case of artificial intelligence. To start with, we will look into certainty factors, because we have seen a glimpse of those. So, our lecture today will deal with reasoning under uncertainty. That means, when there are different types of uncertainties, what are the different ways in which you can deal with that? To start with, we will be talking about certainty factors. Now, to start the discussion, to motivate you, I have just put in some example which is rather interesting. Let us look at the example. We call it the doorbell problem. The doorbell rang at 12 o'clock at midnight. Now, the question that we want to answer: was someone there at the door? Was there anybody at the door? And Mohan was sleeping in the room. Did Mohan wake up when the doorbell rang? Suppose I want to answer these two questions. So, my fact is that the doorbell rang at 12 o'clock in the midnight. Now, so the propositions, if we place it in the form of the logic form that we have already seen, at door X, that means if someone is at the door, then he rings doorbell. And there is another proposition: if there is doorbell, then that wakes up Mohan. All right, this should have gone here. So, wake Mohan. So, these are the two propositions. If someone is at the door, then he rings the doorbell. If the doorbell rings, that wakes up Mohan. Now, the problem is, suppose the doorbell rang. We know that by the first proposition, at door X implies doorbell. We know that. If someone is at the door, that comes from the previous proposition, at door X implies doorbell. So, the fact is that doorbell has rang. can we say that there is someone at the door? If you recall the classical propositional logic, P implies Q means that if P is true, then Q is necessarily true. But if P is false, then Q may be true or Q may be false. That is the implication, and that is the implication operator we are showing here. So, according to deductive reasoning, if we know doorbell has rung, then we cannot say for sure that there was someone at the door using normal implication, right, because P implies Q means if P is true, then Q is true, but Q can be true even if P is false. So, if Q is true, then P may or may not be true, right. So, according to deductive reasoning, if there is doorbell ringing, then we cannot for sure say at door X according to deductive reasoning, but using our common sense or day to day style of reasoning, often we tend to conclude if there is a doorbell, then someone is at the door. Although according to deductive reasoning that may not be true. Okay. So, this sort of reasoning where P implies, if there is something like P implies Q, if there is something like P implies Q and we find Q is true, then we infer P. This may not be correct according to deduction, but that is what we often do, and this sort of reasoning is known as abductive reasoning. Till now, we have seen mostly deductive reasoning, but in real intelligent systems often we take recourse to other forms of reasoning, and all of you will realize and appreciate that when there is a doorbell, then obviously we immediately assume that there is somebody at the door. So, this sort of reasoning, given this sort of P implies Q type of implication, is known as abductive reasoning. And whenever there is a doorbell, you expect that someone is at the door and you rush to the door to open it. Most of the time you are right, but always you may not be right, we will see that. So, this sort of reasoning is also very useful, abductive reasoning. Maybe at a later point of time we will discuss about some other form of reasoning which is known as inductive reasoning. We have not yet discussed that. Okay. So, this gives me an opportunity to just introduce abductive reasoning to you. But then you may ask that, well, if there is a doorbell, then obviously there is someone at the door, but no. The doorbell might start ringing due to some other reason, although less probable, although mostly that will not happen, but still it is possible that the doorbell has rung for short circuit, maybe because of wind, or maybe the dog or some other animal just pressed around the doorbell or whatever. There can be 1001 reasons for that. Okay. So, what to do? If how do you go about inferring these things? Again, coming to the second question, given doorbell, can we say that wakes Mohan up? Because we have already seen that a proposition is doorbell implies wake Mohan. Now, this is deductive reasoning, right. Now, we have got the doorbell. So, the P part of P implies Q is true, therefore, obviously, it will wake up Mohan. And deductive reasoning immediately tells you that. So, it should always be true, but if you think a little bit, we can infer that the doorbell wakes up Mohan when this implication is true. Doorbell implies wake Mohan, wake up Mohan. Only then we can say, if this entire implication is true, that whenever there is a doorbell, that will wake up Mohan. If that is true, then obviously the doorbell will wake up Mohan. But now we can also put this rule or this implication in question. Is this implication doorbell implies wake up Mohan always true? Maybe. There may be cases that when Mohan is really tired, which is not always the case, mostly that is not the case, but if Mohan is really tired, then even a doorbell will not wake him up. Even if the doorbell rings, Mohan may not always wake up. So, this implication that we are saying may be mostly correct, but may not be always correct. So, therefore, we cannot answer either of the questions with certainty. What are the questions? Is someone at the door, or did Mohan wake up? None of these we can answer with certainty. The first one we cannot answer with certainty because that is an abductive reasoning. Most probably the doorbell rings only when someone is at the door, but there may be short circuit cases and all those relatively unnatural scenario which can also wake up Mohan. The second one, does the doorbell wake up Mohan, cannot also be done with certainty because mostly a doorbell wakes up Mohan, but this implication is not always true. Sometimes it may not work. Now, proposition 1 was incomplete, right, because the doorbell can ring mostly because of at door X, but there can be several other reasons like short circuit, wind, etc. Okay. Now, we could have modified the proposition in this way. We can add on different other conditions at door X or short circuit or wind, etc., etc., etc. But it really does not help because there may be 1001 reasons, and how many reasons will you go on enumerating in order to make a complete proposition? That is not always possible, mostly that is not possible. So, this approach does not help because the list of possible causes here are huge. In fact, they can be infinite. Okay. Now, the second proposition, what was the second proposition? The second proposition was a doorbell implies wake up Mohan. That is often true, mostly that is true, but that is not a tautology. Tautology means what? Tautology means something that is always true. If you recall, we had earlier given examples of tautology like say mortal X or not mortal X. Okay. That is always true, irrespective of any interpretation. So, these are called tautologies, A or not A. Okay. This which is always true Now, these things are known as tautologies. Okay? These are known as tautologies. So, proposition 2 is often true, but is not a tautology, it may not be always true. So, how to deal with this scenario? Is there any way out? But this sort of problems like the doorbell problem are very common, and in fact, most of the real life problems that we try to solve using artificial intelligence techniques are like this. Real world is like this. It is always not 2 plus 2 equal to 4. So, in AI we often need to reason under such circumstances, and in order to solve it we need to properly model uncertainty and impreciseness. There is a subtle difference between these two words, uncertainty and impreciseness. Uncertainty in a fact, uncertainty in a rule. It rained, it will rain tomorrow, it will rain today, it rains in July. These are the statements which are uncertain, because although mostly it rains in July in the eastern part of India, say, but or in many parts of India, but it is not always certain that every day in July it will rain. So, these sort of statements are always associated with some sort of uncertainty. On the other hand, impreciseness is inherent in most of the statements that we make. The boy is quite tall. It is quite likely that it will rain in July. What do you mean by quite likely? The boy is very tall. What do you mean by very? Now, I like him very much. How much do you like him? 5, 10, 15? Now, these are not precise statements. The height of the building is, say, 20 feet, 200 feet, whatever. Then we quantify that, and that is precise. But mostly, many of our statements that we make are not precise. So, in order to deal with real life problems, we have to handle both uncertainty and impreciseness, and that can be handled using appropriate reasoning techniques, which we will try to see today. Now, let us look at the different sources of uncertainty. We have seen that doorbell example. So, implications may be weak, they are not absolutely certain that if there is a doorbell, then that will wake up Mohan. We can rather write the implication in this way: doorbell 0.8 implies wake up Mohan. That means, now this implication is being given a strength of 0.8. What does it mean? It will mean, it may mean that 80% of the time the doorbell rings, Mohan wakes up. Okay. So, if I had written doorbell implies wake Mohan, then that is a certain proposition, that is every time the doorbell rings, Mohan will wake up. But since that is not the real life case, we are putting up some quantification of the frequency with which the rule applies. This rule is mostly applicable in 80% of the cases. So, I write down 0.8. Okay. Now, imprecise language like often, rarely, I rarely meet Tom. How frequently? Okay. Sometimes, all these statements, all these typical words that we use in our day to day life leads to impreciseness in the statement. Now, in order to really work in the AI area, and to develop real applicable systems, we have to quantify these terms, these imprecise terms, in terms of frequencies might be some way. One possible way is to code them in terms of the frequencies. We will see the other ways also. And also, so first thing is we need to quantify them, and also we need to design rules for reasoning with these frequencies. All right. We have to deal with the rules. We have to write rules in such a way that these uncertainties are captured in those cases. This is one source of uncertainty. Implications may be weak. There is another source of uncertainty. It is really difficult to get precise information all the time. We have to live with imprecise information. See, whenever we hear some sound, somebody speaking through the telephone, the words are propagated as waves through a telephone line, through a channel where there is a lot of noise, and there may be some words which are wobbled up, and we are intelligent to really understand what that letter was or what that sound was, even if that sound is disturbed or changed during transmission, okay? Because we cannot expect a noiseless channel to propagate the wave. Therefore, to get the precise information is always difficult. In the earlier case that we have seen, say, when does the doorbell ring? In order to code that, if we had to really make it very precise, we had to write down so many things at door X or short circuit or wind, etc., etc., etc. That is not possible. So, that is another source of uncertainty. Another problem that can occur is incomplete knowledge. Knowledge, as we say, is always complete, always incomplete. There is no end to learning. Whatever knowledge you put in your knowledge base, that is never complete. You may learn something new tomorrow, okay? But even if whatever knowledge we put in our knowledge base and we start working with that, our knowledge base will be incomplete and we will have to live with it. We may not know or guess all the possible antecedents or consequence. Maybe I thought that, okay, the doorbell rings besides at somebody being at the door, short circuit or wind or animal, but there can be some other reason. The bell rang due to some spooky reason. I do not know what, but something. I really do not know what. I do not know. That means my knowledge is incomplete there. For some other reason it happened. So, in order to build a system robust, reasonably good and mimicking human, at least trying to mimic human intelligence, we have to deal with such incomplete knowledge. The third source of uncertainty comes from the fact that there are conflicting information. You take a patient with some complicated symptoms. You go to two different doctors. It is quite likely that the two doctors may differ in their opinion, if the disease is not a run of the mill regular things that we see, some very new peculiar symptoms that we have seen, and that there are different groups of doctors who may differ in their opinion. So, experts often provide conflicting information, because the actual truth is not known with certainty. I may make some statement with some belief from my experience, I put in that statement. I say I am 80% sure that this patient is suffering from thalassemia, okay. But that 20% I am not sure. So, another doctor can say, well, I am 70% sure that the same patient, this patient is suffering from some other disease. Maybe actually both the diseases may be there in the patient, or either of them, of these experts, may not be correct. So, that is the reality. So, experts often provide conflicting information. So, when the doctors or the experts speak about these, they speak with a degree of belief. So, we have to quantify the measure of belief, how strongly you feel about what you are saying. How much sure are you? It may be 80%, it may be 70%, but how much sure are you? That is measure of belief. And there is another problem here, that uncertainties are often propagated. What do I mean by that? Say, I had a scenario that A implies B and B implies C. If I perform chaining and suppose A is true, then I come here and take this rule and infer B, and since B is true, I come to this rule and infer C. This is chaining, and in each of these implications that I had here, it was a certain implication. So, it was with a belief 1 and this was also with a belief 1. But now, if I say that A implies B with some certainty 0.7 and B implies C with some certainty 0.6, with some belief 0.6, and I know A, then obviously the strength of belief with which I know B is less than it was here. And again, so I infer B with a less belief, and then I come to this rule and propagate. So, this thing is propagated, right. This lack of belief is propagated here, and again this rule is not certain because it has got a strength 0.6. So, I infer C with even weaker belief, right. Now, let us take another scenario. That A implies B, the strength of belief is 0.7 and A is known with some uncertainty here. I am sorry, this part is not visible. A is not known for sure. Suppose A is known with some certainty of 0.8. Now, here this implication is a weak implication, and further this antecedent is also not surely known. So, the strength with which B is inferred is also weaker than either 0.7 or 0.8. So, if I had B implies C, then with some belief of say 0.8 this implication, then through this chain of reasoning C will be inferred with a much weaker belief. This is what we mean by propagation of uncertainty. This is known as propagation of uncertainty. So, in the absence of interdependencies of propagation of uncertain knowledge, increases that uncertainty of the conclusions increase. Let us look at this example. Suppose I know tomorrow is sunny, will be sunny with a belief 0.6, and tomorrow will be warm, I know, with a belief say 0.8. Now, when I take them together, tomorrow is sunny, tomorrow will be sunny and tomorrow will be warm, what will be the certainty of this conjunction? This is a conjunction of these two uncertain statements, uncertain propositions, tomorrow sunny, tomorrow warm. When I take them together, what will be the my strength of belief in this conjunction? Now, in order to handle such scenario, certainty factors were proposed. This was proposed along with the development of mycene, which we had talked about in the last lecture at the Stanford University. So, this is often known as Stanford certainty factors, Stanford certainty algebra, etc. We will see how we deal with certainty factors. Now, let us have a relook at the mycene rules. If say one rule I am looking at, the first antecedent is if the stain of organism is gram positive, we had seen this rule in the last lecture, and the morphology of the organism is coccus and the growth conformation of the organism is clumps, then there is suggestive evidence 0.7 that the identity of the organism is Staphylococcus. So, the experts could conclude that the organism is Staphylococcus with a belief of 0.7, okay, assuming that all these three are true, all these three antecedents are true. Now, this 0.7 is what we will be discussing about. This is the certainty factor. What do certainty factors mean? Now, it is an expert estimate of the degree of belief or disbelief in an evidence hypothesis relationship. We will be dealing with this sort of relationships now for a while quite frequently. E implies H. That means, given this evidence E, we can conclude this evidence leads to this hypothesis H. H stands for the hypothesis and E stands for evidence. Now, if we go back to the earlier rule, where from this value did this value come? This value actually came from the expert's knowledge and subjective estimate of the relationship between the occurrence of these symptoms, stain of organism being gram positive, the morphology of the organism being coccus, and the growth of conformation of the organism being clumps. These three relates to the organism being Staphylococcus with a strength of 0.7. So, this is a subjective estimate, subjective, we are saying here subjective probability estimate, subjective probability estimate provided by the expert from his or her experience. So, this is this 0.7 is actually a measure of belief. We will write also in this way. MB means measure of belief of the hypothesis H given the evidence E. I repeat, the measure of belief in the hypothesis H given the evidence E. Okay. Now, we can similarly a rule, say in this rule we were supporting, this rule is supporting the fact that the identity of the organism is Staphylococcus. So, this is a measure of belief. Similarly, there can be measure of disbelief, which I would have written MDHE, measure of disbelief. Say an evidence E relates to the hypothesis H with a negation, that is, I do not believe that given this evidence this hypothesis will be supported. So, something like not H, if E tells not H with some strength, say 0.6, then we can say measure of disbelief in the hypothesis H given the evidence E is 0.6. All right. And say this is, let this be evidence E1, and there is another, so there is E1 and some other expert given this E1 says this H with say 0.8, then the measure of belief of H given E1 is 0.7. Now, certainty factor CF of H given E is measure of belief in H given E minus measure of disbelief given H given E. So, in this peculiar case it will be certainty factor will be something like 0.8 minus 0.6 equal to 0.2. So, certainty factor, we will show that later, is a measure of belief minus measure of disbelief. Now, so a rule can either say in favor of a hypothesis or against a particular hypothesis. This a measure of belief like this is in favor, whereas this one is against. So, this is leading to MD, this is leading to MD, whereas this is leading to MB. All right. But the situation becomes a little more complicated when we have got more than one rules contributing to one hypothesis. Say there is a rule here A implies C, and there is another rule B implies C. Now, both these rules are pointing to C, but with different degrees of uncertainty, different degrees of belief and disbelief. So, this is the case A, several rules contribute to one hypothesis. This one is the case. The second problem that can come up is, what is our belief in if several propositions are taken together? What is the belief if several propositions are taken together? For example, here A is a proposition which is an uncertain proposition, and B is another proposition which is also an uncertain proposition. If I take them together, A and B, what would be my combined certainty about this? Obviously, that will be less. The third case that can occur, what is our belief in the result of rule chaining, which I was showing a few moments back, that there is a rule A implies B with some uncertainty, maybe in A, in this fact itself, or in the implication itself. So, there is some uncertainty here and there is some uncertainty here. So, when I chain them together, what would be the certainty in this result C? Obviously, that will be even weaker, but how do we compute that? Because ultimately, we want to find some sort of a computable value. So, these are some typical cases which we will have to deal with. Now, certainty algebra, let us introduce that. It is a heuristic or rather expert given approach for reasoning with certainty. So, measure of belief, let us introduce them. Measure of belief MBHE. Now, here you may face some notational problems. So, let me again clarify that. Say when we write MBHE, that means MB in H given E. That means, if E is known, then what is my measure of belief in H? The same thing is written as MB H given E. These two are equivalent, all right. The same thing is meant by both these notations. So, let us not get confused with this variation of notations which can happen at times. So, measure of belief MB H given E, what is that? It lies between 1 and 0. Okay. If MD of H given E is 0, it will be some number. Measure of disbelief is again between 1 and 0 when the other one is known to be 0, and certainty factor of H given E is MB minus MD, which we have just now discussed. All right. So, we start with a measure of belief which is MBHE. You see the variation of notation because I did it on different days. Measure of disbelief is MDHE and certainty factor of H given is MBHE minus MDHE. I hope this part is clear. Now, there may be multiple evidences, which are supporting the hypothesis H. I am given some measure of belief of H given E. Now, I can have additional evidence like here H is supported by E1 as well as E2, and there are different strengths of relation. E1 is supporting H to some degree, E2 is supporting H to some other degree. Now, how can I compute MB, H, E1 and E2? I hope this is clear. Again, the same scenario, suppose I have got some E1 is supporting the hypothesis H with some strength say 0.7, and there is another evidence E2 which is supporting H with some other strength 0.6. Now, what is my combined belief in H? That is what I want to know when I take both these evidences together. So, what I want to know is what is my measure of belief in H given E1 and E2. Now, obviously, if the measure of disbelief in H given E1 and E2 is 1, that means it is E1 and E2 taken together certainly makes me to disbelieve this, then obviously this one is 0. Otherwise, what will happen? What is that otherwise part? Otherwise, I will compute it as MBH E1 plus MBH E2 times 1 minus MBH E1. Let us try to understand this in a different way. Think of a space. This is my measure of belief in H given E1, all right, and independently let me select another color. This is my measure of belief in H given E2. Now, what is my total belief given E1 and E2? That would be this space, right, that would be this space. Now, what is this space? This part is MB H E1. This part I add, sorry, this part I add is MB H E2, this blue part, but there is a part which is common here. So, I must subtract that, and what is this part? This part is coming twice. So, I will not take this entire part, but a part of that. So, times I multiply this with 1 whichever is falling over here minus MB H E1, right. If you are not sure, I will just do this part again. Say, I can write this part as MB H E1 plus MB H E2 minus MB H E1 MB H E2. This part is common, this is the common part here. So, if I take the common part out, so it will be MB H E1 plus MB H E2. If I take this out, then this part will be 1 minus MB H E1, right. That is the expression. Therefore, let us go back. So, this is the formula. Look at this formula carefully. Now, similarly, for MD, measure of disbelief will be similar. MD H E1 and E2 will be 0 if the measure of belief is 1. Otherwise, it will be MD H E1 plus MD H E2 times 1 minus MD H E1. Okay. So, the combination of hypothesis. Now, the earlier one was combination of evidence. Now, we are looking at combination of hypothesis. Now, this is a little different. So, what did we discuss? This the earlier part. This is the combination of evidence. When there are more than one evidences, what is our strength in the hypothesis? Next thing that we want to see is the if there be multiple hypotheses H1 and H2 given E supports H1, E supports H2 with different strengths. Now, what is the common? If I take the conjunction, what is the strength of that? Now, this is minimum of MB H1E and H2E. That means what? That means our I have got a hypothesis H1, I have got a hypothesis H2, one evidence is supporting this and the same evidence is supporting this with say 0.7 and this with 0.6, and I want to find then E is supporting H1 and H2. What is the strength of that? It will be the minimum of these two links, the weaker of these two links, because both these will be true with the minimum value. So, this will be 0.6. Similarly, if I had taken OR is implying either H1 or H2, then obviously this majority part will come here as 0.7. So, that is the formula that measure of belief of H1 and H2 will be the minimum of the individual beliefs, and the disjunction H1 or H2 will be the max of, I missed again another bracket over here, of these two. Now, disbelief will be computed analogously in the same way. In place of MB, it will be MD. Now, this is needed for calculating the certainty factor of a rule and rule antecedent, where there are several clauses. We will see that later. The other thing that remains here is chaining of rules. Okay. We have seen this chaining of rules several times. Now, let M be prime H S. S is a symptom and M be prime, note this prime, be the measure of belief in H if we are sure about S. But if we are unsure about S, because S has been inferred by another evidence E. So, E led us to believe S, and that was not certain. So, there was some weakness over there. So, when I do not have full confidence in this, then this M B prime will have to be modified. M B prime is the measure, the belief in H if S is known for sure, but S is not known for sure. Therefore, given the uncertainty in S, we will have to modify the M B prime with in this way, that will multiply it with max of 0 and certainty factor of S given E. Whatever this one is, if this is 0, then this will be 0. This entire thing will be 0. If S is not known for, if S is known to be false for sure, then this will be 0. Otherwise, whatever is the certainty factor here, that factor will multiply m b prime to give me the measure of belief in S. So, we stop at this point today, and in the next lecture we will take it up from here and we will further take some examples of certainty factor, and then we will move to probability. Certainty factors. In this lecture we will further deal with that. We have seen the different scenarios. So, we will first start with the last point where we left, certainty factors in the case of rule chaining. Now, what was really attempted to be explained here is something like this, that I have got some antecedent A pointing to some other antecedent B with some certainty, say 0.7. All right. This is equivalent to writing it as A implies B 0.7. What does it mean? It means that if A is known with certainty, if A is known with certainty, then I will infer B with a confidence or belief of 0.7. So, I would say that M B of B given A is equal to 0.7, all right, in the normal case. But we know that this A may not be known with certainty, right. There may be some uncertainty in this A itself. If the certainty factor of A given whatever evidences E be 1, in that case it is a certainty. But suppose if the certainty factor of A given some evidence E is less than 1, then obviously this 0.7 that I get here should be modified. Therefore, we say it is M B prime. M B prime